Yeah, there you go. Is it like red? Like a little, okay, very good. I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I just thank you for the students. Pray that you're with us today as we begin our study of chapter 11. Just guide our thoughts and help us to make the most of this time we have, Lord. In your name I pray. Amen. All right, so language becomes more important at this point. So there are some abbreviations I'd like to use with meaning. These are at the start of my notes. This backwards E means there exists. If you put a slash through it, it means there does not exist. I sometimes use this as with respect to, left-hand side, right-hand side, pretty self-explanatory. This means X is inside the set B, or X is an element of B. This means A implies B. This means A if and only if B. So these are equivalent statements. This means therefore. I don't use that one too much. This is for all. Upside down A is for all. This means definition. Sometimes it's used as an identity. It's approximately. You've seen me use equation, solution. This is counting numbers like 1, 2, 3, 4, natural numbers, right? Q are rational numbers. These are quotients of integers where the denominator is non-zero, right? And then you've got real numbers and complex numbers, all right? So I'm going to start out today just by talking a little bit more about what is a real number, because that's really the heart of chapter 11. We're talking about, ever since Matthew knocked my computer over I'm never really sure if it's charging or not. Let's see here. So we're actually going back to basics here for a minute. I'm trying to get through this without too much writing. Come on. Wrong chapter. Sorry, guys. I forgot to tell you to take your Dramamine. Here it is. So this right here, guys, is an attempt. Well, no, I mean it is a suitable definition for what real numbers are, right? You can say, well, what is a real number? I can tell you this much. A real number is something that satisfies these axioms. If you've got two of them, you can add them. You can add them in either order. Addition commutes. Addition is associative. There's something called zero, right? For every real number, there's something else minus the real number that you can add to it and get zero back again, right? There's a notion of multiplication. It commutes. It's associative. There's this thing called 1, right? If you multiply the number 1 times any other real number, what do you get? Number again, right? So 1 is the multiplicative identity, whereas 0 is the so-called additive identity, all right? Now, if you look at it, if you just look at axioms 1, 2, 3, 4, 5, 6, and 7, if you just go this far, right? If you think about it, integers also satisfy these axioms, right? Is the sum of integers an integer? Is the product of integers an integer? Indeed, it is, right? Is 1 an integer? Yes. However, if you look at 2, is there a multiplicative inverse of 2 in the integers? Well, no, the multiplicative inverse of 2 is a half, right? That's not an integer. So that was why integers are different, for one thing. So axioms 1 through 8 altogether, plus axiom 9, which is this. Axiom 9 also holds for integers, but not axiom 8. All of this put together, axioms 1 through 9, give you what's known as a field. All right, a field is just a set which has a multiplication and addition which behave normally, such that every non-zero thing has a multiplicative inverse. That's all a field is. So like rational numbers are a field, real numbers are a field, complex numbers also a field. Real numbers are really special though because they're also a totally ordered field, meaning there's a notion of less than or equal to or greater than or equal to, right? And if you have A less than or equal to B and B less than or equal to A, that forces A to be B, A to be equal to B, right? And you have this transitivity, totality. Now 11 is really the thing we're going to be grappling with the most in the next few lectures is this least upper bound property. Here's the least upper bound property. Every non-empty subset of the reals has an upper bound. That has an upper bound. Yeah. Has a least upper bound. This is also shaking for you guys, right?
Yeah.
Okay, it's not just me. All right, good. So this makes the real numbers complete. In fact, what I'm defining here is, there's another way to define complete, I suppose, but this axiom 11 is a little bit more esoteric, right? Like, what is this least upper bound property? All right, so that's what we're going to try to understand here today. And also, what is a sequence, and we'll work with those and so forth. So we put this away. I just didn't want to write that out. So that's in the notes that I posted, right? But I think you guys know what a real number is anyway, right? Yeah? But do you know what it is? You know, how do you construct a real number? That's a harder question. So let's talk about upper and lower bounds. So roughly speaking, we're in section 11.1. Let me just take a second here to give you the big picture of where we're going. We're studying the least upper bound property so we can discover a couple of pretty careful theorems about sequences and the convergence of sequences, all right? And so chapter 11 is just about sequences. A sequence is what? A series of numbers. Unfortunate terminology, but correct common terminology, but we would not want to say that soon. So yeah, it's a list of numbers that are put in order, right? So that's basically a sequence, just an ordered list of real numbers for us as a sequence. And we'll talk about when a sequence converges or when it doesn't, and develop theorems to study that, right? That then leads to the topic of series in chapter 12, which is a different thing. It's a sum of things, an unending sum of things. To understand a series properly, you need to know what a sequence is. And then our ultimate goal, past series, is to study what are called power series. Power series give us a way of understanding functions in a new way, and it gives us a systematic way of approximating things and doing calculations that we couldn't do before. So power series are really important, and ultimately that's what we're building towards. But the journey is also important. Like everything we're learning about sequences will help you grow in your understanding of math. Okay, so let's get to it. At least in upper bounds and lower bounds. So let's let S be a subset of real numbers. Then M, little m, is a lower bound of S if what? If M is less than X for all X in S. Let me put that in words. It's a lower bound if it's a number which is smaller than every number in the given set. What did I not say about M? Does M have to be an element of S? No, not at all. So let's see here. We can draw a picture, right? Was it?
What is upside down AB?
For all?
For all.
Yeah. So if S is, for example, this set, let me draw it in color. So if S was this thing, I can illustrate it with a number line here. Suppose this was S. This, and then it's also this point, and this point, and this point, whatever, all right? And there's a bunch of points in here. So S could be all kinds of wacky stuff. M is a lower bound. All that means is if we picture it on the number line, it's like over here somewhere, right? Okay. Now, if let's say I need another letter. No, one. Thanks. Let me just get to it. The greatest lower bound is denoted GLB of S. So if I said this thing was equal to n, right? Well, let me just not say it that way. What can we say about the greatest lower bound? If m is any lower bound of S, then m is less than or equal to the greatest lower bound of S. So you can kind of see in my picture for the example that I drew, right? You can kind of visualize what the greatest lower bound is, right? So if that's a hole, right there would be where the greatest lower bound of S would be, right? You see that? Does the greatest lower bound have to be an element of S? Well, not necessarily. Now, if the greatest lower bound is actually an element of the set, right, then it has a special name. If the greatest lower bound of S is an element of S, then we write that the greatest lower bound of S is equal to the minimum of S. All right. So that would be the minimum value in S. Does that make sense? But if it's not, I mean, when we write min, we're expecting it's something in S, all right? Now, I think you see where this is going. We can also talk about what? Not the lower bound, you can talk about the upper bound, right? And so the greatest upper bound, excuse me, not greatest upper bound, that's harder to find. Let's see here. So I'll do it again here. Let S subset of R, then S marker's worthless. I'll use a big M with feet. Is an upper bound, all right, of S if big M is greater than, oh, did I say it? There's a mistake over here. Excuse me. This could be what? This could be less than or equal to. Okay. So it's an upper bound if m is greater than or equal to x for all x in the set. If, well, let me just say this. There's point number one. Point number two, we denote the least upper bound. Least upper bound by lub of S. And it's just what it sounds like, all right? What does that mean? If M is upper bound of S, then the least upper bound of S is smaller than or equal to M. Finally, one last point, terminology-wise here. If the least upper bound of S is an element of S, then we write that the least upper bound of S is actually equal to the max of S. I should tell you, there's another popular naming conventions for these things. Like other books, myself included, would sometimes say that the least upper bound of S is called the supremum of S, or sup S. It's the supremum. I kind of like that terminology. It just gives me the right idea for some reason mentally. And the greatest lower bound of S, another popular terminology for this is that it's the inf of S. It's the infimum. Infimum. I can't spell it, but anyway. So it's the inferior. You know, it's the superior. Now, again, they don't have to be in the set, but they're the, you know, the smallest possible upper bound, the greatest possible lower bound. That's the idea. Let me show you an example. Let's look at the set, which is defined to be 1, 1.1, 1.1, I said 1.4, sorry. 1.4, 1, 4, and so forth and so on. Here, these are the decimal, truncated decimals of what? Square root of 2, right? The square root of 2 is what? 1.414 da stuff, right? It's not repeating, right? You could prove if it was repeating, that would make the square root of 2 a rational number, which is impossible. That you could also prove. So, this set. Can you guys tell me what's the least upper, like, can you tell me the least upper bound and greatest lower bound? Least upper bound and greatest lower bound, what's, I'll do the easy part. The greatest lower bound of this set S I just invented is 1. Okay. There you go. That's also equal to the minimum of S. How about the other one? What is the least upper bound of S? Least upper bound of S, or the supremum if you like, is the square root of 2, right? Now that is, of course, not an element of S, right? No matter how far you go, you never get to the square root of 2, right? You get closer and closer, but you don't get there. In fact, S is a subset of what kind of numbers? Let me rewrite this in a slightly more suggestive way. This is 1, that's 14 over 10. This is 1,414 over 1,000. You get the idea, and so forth, right? Oh, I'm sorry. I no wonder you guys are mystified. I missed something in here, right? It's 1.4. What was the next thing? Good grief. 1.414. Yeah, 1.41. Yeah, I was like, why am I jumping from 10 to 1,000? That's weird. Oh, duh. Okay, there we go. I hope that wasn't confusing you. If that was confusing you, I'm so sorry. But you should, like, you know, speak up. What are those numbers? Those are fractions, right? Fractions of integers. Those are rational numbers, right? S is a subset of rational numbers. Right? Notice that the least upper bound of S is not a rational number, right? This example shows you that rational numbers are different than real numbers. They don't satisfy the least upper bound property. What's the least upper bound property say? it says that every non-empty subset of real numbers has a least upper bound which is a real number. The rational numbers fail in this regard. There's a subset of rational numbers that has a least upper bound, and yet that least upper bound is not a rational number. Right? So this is something different about real numbers versus rational numbers. Rational numbers have holes. Right? There's a square root of there's square root of 2 shaped hole in the rational numbers at the square root of 2, you know? It's right there. So this notion of completeness is subtle, all right? But basically the notion of completeness for real numbers says that there's no holes in the real number line. There's always a real number there, no matter how far you zoom in. There's no jumps. In some sense, the completeness axiom says that the real numbers are continuous. They're stuck to each other in some regard. There's also a greatest lower bound property, all right? What do you think that says? It says that every non-empty subset of the reals, can't spell, subset of reals, which is bounded below has a greatest lower bound, and which is in the reals. That's not an axiom. You can actually prove that follows. It's a theorem. You can prove that once you have the least upper bound property, the greatest lower bound property follows suit. We could prove that. Yeah. Did I do that? Every non-empty subset of real numbers. Ah, yes, thank you. Goodness gracious. Yeah, this is very important. Right here, I'm supposed to say which is bounded above. Right? Otherwise, it's not true, right? Let me show you some examples of that. So like example, if I look at, for example, 0 to infinity, which is what? This is x in the real numbers, such that what? X is greater than 0. Or if I look at, say, minus infinity to 2, which would be what? That's x in the real numbers, such that x is less than or equal to 2. So on the left-hand side, guys, I have interval notation. On the right-hand side, I'm using what's called set builder notation. All right? So this is not bounded above, right? And this one is not bounded below, right? Okay. Fun. All right.
So, can you explain why the square root of 2 is a gap in the number line?
Well, I didn't say it was a gap in the number line. I said it's a gap in the rational numbers. I mean, yes, can you find rational numbers that are arbitrarily close to the square root of 2? Sure. But are they the square root of 2? No.
Because it just repeats it.
The square root of 2 is not a rational number. So. Sorry. Let's see here. Let me see if I can come up with some other examples for you guys. How about this? Let's let s be equal to 1 over n such that n is a natural number. Can you guys tell me what the least upper bound or greatest upper bound of this thing is? If there are any. I mean, is it bounded above? Is it bounded below? It helps, I guess, for me to write this out like this. This is really what? 1 half, right? 1/3, 1/4, 1/5, dot, 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 right? You probably can tell me what's the maximum of s actually. Which of course is also the greatest lower bound. What's that? It's 1, right?
Oh.
And let's see here, what would be the greatest lower bound of s? Zero. Yeah, we get close to 0, but we don't get there. But if you tried to make it something larger than 0, I can always find some 1 over n which is smaller than that, right? If you told me that the greatest lower bound was like epsilon, I can find a 1 over n which is smaller than epsilon, whatever epsilon is, right? Does that make sense? Another example. How about s equals to, say, inverse tangent of n, such that n is an integer. Sorry it takes so long. It takes me a while to describe this idea, and it's really foreign to your way of thinking, right? So, and we're not really solving a problem, right? I'm just describing an idea. So I know this is weird to you, right? Because we've been in problem-solving mode all semester. We're not in that anymore, all right? We're in discovery format mode for a while here. So you need to adjust. If you're waiting for me to solve a problem before you pay attention, that will make you fail this part of the course. Don't do that. You need to try to engage in what we're doing and try to understand what it is that we're trying to understand. Just a warning. Excuse me. Now, I am going to try not to be as proofy as I was last year. But I can't avoid certain things. Like, we have to discuss this. It takes a while. So this here is what? You could look at it as, one way you could write this would be like inverse tangent of 0, right? If you wanted, you could think about it in terms of plus or minus notation. It's like plus or minus inverse tangent of 1, right? Dot, 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 dot. Plus or minus inverse tangent of 1,000. Dot, 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 plus or minus inverse tangent of Donald Trump's net worth. Whatever you want. Here, 10 to the 6, because, whatever. Let's see here. Anyway, you guys tell me, what is the inverse tangent of a very large number? Pi over 2. But yeah, 90 is kind of right. So you're right, like these are going between, anyway, we have this identity from our study of trigonometry, minus pi over 2 less than tangent of x, right? Less than pi over 2. And this is true for all x in the reals. This is something we know about inverse tangent, because the vertical asymptotes of tangent flip the horizontal asymptotes of the inverse tangent. It never gets to plus or minus pi over 2, right? But approaches it. And so you can see that the greatest lower bound of s is going to be minus pi over 2, whereas the least upper bound of s is going to be pi over 2. Neither of those are a min or max, because this set has points which never quite get there, right? There's a few examples. All right. So with that, I'm going to shift gears and go on to our next concept. We'll come back to this and prove a theorem in a future day, so I need to do it. But I need to describe to you what our sequence is, and that's really what we're after here. So, I mean, part of me says that I should do this first and then talk about the, upper bound property later. But I'm just a little bit too sick to reorganize things at the moment. I don't trust myself to do it, so I'm just following the book. We're in 11.1, maybe 11.2 at this point. Let me check. No, 11.1 is just the least upper bound axiom, and the theorem that the greatest, excuse me, it's just the least upper bound stuff. Well, it's a little bit more than that. There's a theorem, 11.1.4 on page 531, which says something interesting. Let me quote that theorem. I won't prove it, but I'll quote it for you guys. It's worth noting. Theorem 11.4.1 says the following: if m is equal to the greatest lower bound of s, and if epsilon is a positive number, right, then there is at least one number s in S, big S, such that m is less than or equal to s, little s, is less than m plus epsilon. The proof actually involves using the least upper bound axiom, all right? But, I'm going to go on here. I just want to draw a picture to illustrate this. So what we're saying is that if we have the set S, right? Which I'm going to just make the set I'm going to illustrate the set with my picture here. So it could have gaps in it, right? Could have like a bunch of discrete points like that. Who knows? The set could be whatever. But the point is, m is equal to it has the greatest lower bound, right? So in my picture, the greatest lower bound might be this, right? Right there. And then it says, if epsilon is greater than 0, right, there is at least one number in S such that what? M, this is my M. So what would m plus epsilon look like? M plus epsilon would be some point over here, right? Here's m plus epsilon. Epsilon, some positive number. I don't know what it is exactly. It says that there's at least one S in S such that S is between what I did in red and what I did in green. Does that make sense? So there's some S in here somewhere, like that. Yep. That means that you can always find some point between the edge of S and m plus epsilon if it's got a lower edge. There's a similar theorem if you had a least upper bound, like over here, if you had like a big M equals the least upper bound of S, right, you could look at something like M minus epsilon. And likewise, there's a theorem that says, you know what, you can find at least one point over here, like this, x, such that M minus epsilon is less than x, is less than the least upper bound, well, M. All right, so there also exists a point like that. It could be that the x or the s on the other side are actually just the least upper bound or the greatest lower bound, respectively. That's possible. But anyway, we could prove that, but you know, I think it's geometrically pretty obvious that these things are true. Yes, but you can actually prove them carefully, and that's done in 11.1. All right. So sequences. Let's talk about sequences. So, what is a sequence? Definition. A sequence in X is a function from the natural numbers to X. I'm being intentionally vague. You could talk about a sequence of rabbits. Talk about a sequence of children. You could talk about a sequence of politicians. You could talk about a sequence of light bulbs. You could talk about a sequence of pizzas. You get the idea. I mean, sequences can be whatever you like. Now, we're mostly interested in the case that X is equal to the real numbers, on rare occasion, the complex numbers. So if X is equal to R, then we call it a what? A sequence of real numbers.
What's the hourglass looking?
It's just X. If it's bothering you, here. There we go. Fixed it. All right, there we go. Whoa, fun. So, there are different notations for this, right? So, one notation you could use would be like f is a function from n to the reals, right? That would be a real sequence. But we don't usually do that. Instead of writing f of n, we don't usually we usually use, well, instead of writing f of n, we typically write f sub n here, right? And, I mean, so, for example, I could do something like, a sequence is defined by f of n equals to n squared, right? Or, I can write f sub n equals to n squared. Just notation, but this is our go-to notation for sequence, all right? Now, the range of the sequence, what's the range of the sequence? Oh, shush. Quiet, we're having fun. The range of the sequence, it's just me, it's not I'm not being a bad husband. All right, the range of the sequence would be just what it sounds like. That would be, you know, f sub n such that n is a natural number. So like the range of this sequence I'm looking at, this is a more general definition, the range of this sequence would be, and a lot of books identify the sequence and its range. All right? I would like to distinguish between those things, but anyway, so here's the range of the sequence. I got 1, 4, 9, 16, 25, 36, 49, whatever, 64, 81. You get the idea. Anyway. Now, I mean, you could argue, well, that defines the sequence, right? And that's also true. If you give me a list like this, right, that defines if I set the starting point, right, like f sub n, and usually notation n equals 1 to infinity, like that. Right. Give you another example. How about this? Sequence, let's say a sub n equals 1 to infinity, and I'll start it out. You get 1, you get 1, let's see, 2, 3, 5, 8, 13, 21, 34, 55, 89. What comes next? Or did I make a mistake? I mean, you could argue I can't really make a mistake. I'm defining something, but there is something I intended here. 144, how did you get that?
The last one plus 2.
Okay, so another way we could define this is A1 is equal to 1, A2 is equal to 1, and then AN is equal to AN minus 1 plus AN minus 2 for n greater than or equal to 3, right? This kind of definition I just gave right here is called a recursive definition, right? So sometimes, I mean, some sequences are defined by like a slick little formula like n squared, right? Sometimes a sequence could be defined recursively like this, right? There are other stupider sequences. Let me show you one. By the way, what's the name of this one? Yeah, it's the Fibonacci. This was discovered by some 12th century monks studying the mating habits of rabbits on some island in the Mediterranean. Exciting, yeah? All right, so 10, 1. Oh, now I got to think. $13, 5. Oh man, I think 19. What's the next? I'm sorry, guys. I was determined this lecture was going to be more interesting. I need to stop covering 11.1 and just tell you guys to read it. Oh well, it's too late. It's obviously 3. Next is 3. You don't see it. So you have A, B, C, D, E, F, G, H, I, J. So you got 10, 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so this is J, this is A, that's M. I had to work that out over here. That's E. I happen to remember T is 20, so S is 19. So obviously the next is C, right? So I was doing James Cook. I was working on James Cook, but, you know. There are any number of stupider sequences you can define, like this one. Really, your imagination is the limit. I mean, we do this sort of thing with emails. You take a sequence of data, you run it through something called encryption. It makes it much worse than this. This is alphabet code. Very 7th century nonsense, you know.
binary?
You could also look at sequences of binary numbers, sure. But anyway, tomorrow I will show you how to add sequences, multiply sequences, and we will start taking limits of sequences, which is where the fun is. Thanks, guys. If I didn't make sense today, you should just read section 11.1.